We're going to look at properties of ionic compounds. Most ionic compounds are crystals or solids. You can think about ionic compounds such as sodium chloride. Those are crystals, nice, pretty crystals. Now, they can conduct an electric current when they're melted or dissolved in water. Now, solids will not conduct, solid ionic compounds, not solids in general, but solid ionic compounds do not conduct electricity. So, for example, if you have some salt on you, or you're holding the thing as salt, a big crystal of salt, that's not going to conduct electricity. But if you dissolve it in water, that will conduct electricity, because once they're in water, they will break up into their ions. And we have charge here, and with electricity, we can transfer with charge. So that's why if you're ever taking a bath or something, or you're in water, you don't want to have an electric current run through it. Now, ionic compounds have very high melting points. That means they will melt at a very high temperature, and they have high boiling points, and they will go into from a liquid to a vapor in a very high temperature, or liquid to a gas in a very high temperature. They are poor conductors, and we're talking about the solids here, but they're good insulators. And usually, it always follows if you're a poor conductor, you're a good insulator, or vice versa. So here's a crystalline solid, a crystal structure of sodium chloride, and we have the purple spheres are sodium cations, and the green are chlorine, and we see how they're nicely structured in a nice crystal lattice. Because of the different charges, they're able to line up that way. And here's a nice, beautiful picture of a sodium chloride crystal or salt crystal. You know, it almost looks like just a diamond there. So just be careful if someone gives you a big crystal. You think, wow, it's a diamond, but it might just be a big salt crystal, and you go swimming and it just goes away. So ionic compounds, we see this cool little diagram. They don't take stress very easily. It means if we have a stress or some sort of a pressure, they will crack and break. They don't bend as easily, like, for instance, a metallic compound or a covalent compound. They'll break, and so this is what shows how brittle they are. Once there's a stress, the bonds will break. They are not malleable. They're not ductile, they just break off very easily. So we talk a bit about metallic bonding here. I just had to throw in a picture of Metallica. This is early Metallica. We only really have the two surviving members, James Hetfield and Lars Ulrich there. But metallic bonding is a bit different than ionic bonding or covalent bonding, and metallic bonding will give a metal its properties. Metallic bonding is where you have a sea of localized mobile valence electrons drifting freely from one metal atom to the next. So what does that mean? Well, when metal bonds, it's because you have these charges, these positive charges of mobile valence electrons. Mobile means they move freely, they're drifting freely. Valence electrons, so these outer electrons, they're just freely moving around like in a sea of electrons. So here we have these cations, the copper cations, and they're drenched in a sea of electrons. It's just like they're bathing in it, and they're just from one electron to the next, it's just a sea of it flowing freely. And this causes the metallic properties that we know of. So it's a pretty cool graphic. We have these positive or partially positive metal ions, and then the electrons just kind of moving through them, going from one place to the next. That's why their great metal is a great conductor of electricity and heat, because charge is carried on those electrons. The electrons can just go right through. So metallic bonding is because we have these sea of electrons and the positive cations. Because of this metallic bonding, the sea of electrons that these positive ions are in, it gives the properties of a metallic bond. So you see there at the very bottom there's this graphic. If a stress of some sort is placed on a metal, it doesn't break or crack, it just will bend. It will be malleable or ductile. Because of the bonding, the attraction is still there between the positive and negative. And it's because of this, it can conduct heat, conduct electricity. You have high melting points, high boiling points. They are very strong, malleable, can be hammered or pressed out of shape without breaking, and ductile, able to be drawn into a wire. Luster, the shine, that's because of this sea of electrons as well. Opaque, meaning it can reflect light. Alloys are a mixture of two or more elements, one of which is a metal. These are just homogeneous mixture. Alloys are homogeneous mixture. Two or more of these are metals, not always. Now the reason we have alloys is their properties together as a mixture are often superior to those of the component elements. So for example, an alloy of steel, which is iron and carbon, is much superior than just iron alone. So here we have some alloys, homogeneous mixtures. Now bronze metal here, bronze is usually copper and tin, a mixture of that. We have brass here. Brass is usually copper and zinc. Here we have a cast iron skillet. That's usually iron and carbon mixed together. And we have some stainless steel, usually iron, chromium, carbon, and nickel. So these are all alloys, homogeneous mixtures, and they just together they're much superior